Okay, so just a few reactions on what we consider multiple equilibria. So we're going to bring in concepts of the common ion effect, looking at a couple of reactions, but more this time on how to prevent precipitation. Like what do we do in order to prevent precipitation from happening? That if I put some solid in, at what point do I need to make the concentration um, so that the reaction precipitates or doesn't precipitate, right? So in a reaction, so we can say let's just propose a reaction already. So why don't we concentrate or calculate the concentration of H3O plus needed to prevent precipitation of some, how about we use zinc sulfide, right? So let me give you some more information on that. So we'll give you the concentration of zinc ions. So I'll give you the concentration of zinc ions. We'll make this 0.050. And then how about the solid, a common ion here? We use sulfur as the common ion, so we'll say H2S. Some hydrogen sulfide, and we'll put. So we have a couple concentrations here. So by multiple equations, so we should notice, in fact, that um, we are going to have, or recognize that we are going to have um, two reactions from this. Um, the first reaction, we need zinc sulfide. So, and it, should we give? I'll give it. We'll look up the KSPs. Um, we'll look up the KSPs here in a second. Let me get that ready as well. So, um, file, no, that's intro. J. Yeah, so we'll need a KSP for that. Uh, so calculate the hydronium concentration needed to prevent precipitation of zinc sulfide. All right. So we're going to need two reactions. We're going to need to first make the zinc sulfide aqueous. Right. So this will be our first reaction that we're going to take a look at. So we take zinc sulfide as a solid, and then we just make that aqueous and break it up into ions. So we get uh, zinc 2 plus we get some sulfide. The next reaction we're going to need is we're going to need H2S. And you kind of need to recognize H2S here as being an acid, right? So we're going to take a look at that as being an acid. So we're going to take H2S, um, aqueous. We're going to add some water to it like we did in the previous chapters. And we're going to get hydronium, right? And because we're dealing with hydronium, right? Like we need to recognize that that's going to be part of the acid-base reaction that we have here. We got H3O plus aqueous plus just some sulfide. There's our common ion. So a couple things that we recognize here is as soon as we see calculate the H3O plus, the hydronium, if we're going to calculate the hydroxide, the hydronium concentration, is that one of these reactions needs to be an acid-base reaction, right? Um, the other one we would recognize, and I would if this is what we're trying to prevent, we understand that that's going to be a solid, so we're going to need the dissociation reaction for that. So now that we have our two reactions, so let's go ahead and look up the KSP for this. So the KSP for zinc sulfide, Let's see. For zinc. Oh, zinc sulfide is not in here. Let me see if I can grab that somewhere else. For the exam, I would provide this information for you. So let me look up the KSP for that. Uh, all right, so KSP for zinc is going to be 1 times 10 to the minus 27. Uh, and let's see. Now here we're not going to need the KSP, but since we have an acid, right? Since we have an acid here, base here, uh, let's see. This is my acid, this is my base. Let's see if we can get the Ka. So uh, we're not going to need the KSP for that, but we will need the Ka. KSP, KB, and our Ka. Ka is 8.9 times 10 to the 8th, but that's not what I have in my notes. My notes offer something different. Let's take a look at something. My reaction is actually incorrect. My reaction's incorrect here. H2S this involves balancing this. Wow, lucky I provide you guys these reactions on the exam. And that's why this Ka is different at 1.0 times 10 to the minus 26. Since we're doing a second ionization on here, so the second ionization, so the Ka, so this is the Ka2, 1.0 times 10 to the minus 26. So that's why it doesn't. I was kind of curious why this in my notes this does not, um, because it's a second ionization. Um, we go from two to simply just one. So we write that's a second ionization. But for the exam, I would provide this. I would provide these reactions for you. I would again give you this information, and I would give you this information here. Um, and I would also let you recognize that it's a second ionization there. All right, so I guess we can continue now. Unless anybody had any questions, we can continue. So this is kind of a process, a couple of steps in order to figure out what's going on here. So
Yeah, I
yes,
was kind of reading the book,
Uh-huh.
trying, but this chapter was like really difficult to understand, and I don't know where they come up with the equations.
The equations are in the language of the problem,
Yeah.
right?
Okay.
Because we have to have an understanding when you're presented with calculating hydronium H3O plus, when you're presented with calculating um, anything with hydroxide, is that we need to recognize those as being part of acid-base um, reactions, right?
Mhm.
Where we deal with conjugate acids, conjugate bases. In terms of precipitation reactions, right? So it's all just in the context of the problem itself is
Mhm.
how we determine this, right? So if we're given, um, if you're given information regarding, let's say they want to know uh, some calcium hydroxide plus some solution of, let's just say, NH3. Well, we recognize this, that this would dissociate here, that this is a solid, and we have to dissociate that. If we're going to introduce some amount of ammonia, well, I recognize personally, right, we should, I would hope that you guys by now would recognize that this is a base. Well,
Mhm.
that means I'm going to need a reaction for this. And what do we do with this? We always simply put it in water. Whatever we do with an acid or base, we simply put it in water. We don't put it in anything else. We don't put a base in more base. We don't put it in an acid. We simply just take whatever base, base or acid we have, we put it in water, and we get this here. So this is one reaction, and this is solid, where we get another reaction. Here, so it really is just everything we have is just in the context of what the problem is asking you. I won't leave you empty-handed on the exam, right? I won't leave you empty-handed on the exam. Is that you will have some guidance that I on some of them. I've given you the reactions on some of them. I've kind of um, given you some key words to the reactions. Um, but for the most part, that you would have to just recognize by the whatever the problem is discussing on how we would deal. Well, where do I get my reactions from, right? If I gave you
Mhm.
this, right? Let's say I gave you this, and I asked you to calculate the molar solubility. Well, recognize molar solubility means that I'm going to have some kind of solid, so this is probably my solid, and I'm going to have to break this up. I'm going to have to break this up into, oh, here. If I say I'm going to put this in a solution of sodium, right? Here, do you recognize what that would be?
Would that be an acid?
That would be an acid, which means that what are we going to add to this acid here? Because right, we have to remember this is also this is just a spectator ion. So in a previous
Mhm.
chapter, we've already talked about this. If you recognize this as an acid, what are we going to add to our acid for the reaction? We always simply just add water. We get H3O uh, plus we get some. So now I have my two reactions. right? So it just goes by understanding. So there's really just kind of a lot to remember as far as what kind of reaction that we're going to be working with. Whether it's just one reaction, whether we need two reactions, but it's all just in the context of the problem itself. That, would it seem logical at all? Like if I give you this information, if I said H3O plus and zinc sulfide, and some student, there's no excuse for a student doing this. Zinc sulfide plus water, and then I'm going to get H3O plus I'm going to get some zinc, and then try and balance this and go, oh, well, I don't know what like this would make absolutely no sense if a student is looking at this problem and making something up like this that just makes no sense.
Mm-hmm.
um, then there's kind of an issue of maybe studying or not coming to office hours at that point. You know what I mean, Elisa?
Yeah.
Like I
Yeah.
would I
Yeah.
would I would hope that you would recognize um,
Yeah. It wasn't
these.
until you
Yeah,
gave me that example where I was like, "Oh, okay, cool."
yeah.
I was kind
So
of thinking something like that. I was like, "Did he
so we
chose
just
that
take
one
our time.
because
That's why
they
you're
have
you know you're given
hydrogen?"
4 hours. You're given 4 hours for the exam, which is I think plenty of time for the exam, and we just take it slow and just make sure you're reading through the questions. But
Okay.
there's plenty of information in here to decide if you need one reaction or two reactions. Does
Okay.
that help?
Yeah. Thank you.
Okay. No, no problem. No, it's a good question. So here we're asked how much, so we need to calculate this. We need to calculate this concentration needed to prevent this from precipitating, which means we need this reaction to shift to the right. So in order for that to happen, is that we have to let's figure out. So I think the first step here. So we'll just kind of put a step one in here, and we're going to determine the concentration of this common ion here. So we're going to determine this concentration here when Q is equal to KSP, right? Because we are given the KSP here, right? So and we're given the concentration. So we're given the KSP. We're given the concentration. And again, I won't have you guys look up the KSP. I'll give you all the KSP, Ka, Kb values that you guys need for the exam. That there's no need to look that stuff up. Um, unless I'm asking you to calculate it, and then you won't. But let's see what we have here. So our KSP is equal to zinc 2 plus our sulfide, right? And we don't use the solid, so we don't have to put it over anything because it's over a solid. And this is equal to 1 point times 10 to the minus 27. And since we know what the concentration of that is, well, then we can simply just go ahead and replace that and say 0.050 times this concentration is equal to 1. I keep putting 1.0, just 1 times 10 to the minus 27. So the concentration here, let me calculate that, is 2 times 10 to the minus 26. Okay, so when we're calculating this, and we understand that here our reaction needs to shift to the right. Our reaction needs to shift to the right, which means that in order to prevent precipitation, in order to prevent the precipitation, our Q has to be less than our KSP. If Q is less than ASP, then we're going to have a shift to the right. In order for us to have a Q that's less than KSP, any concentration of S2, so S2 has to be less than, S2 has to be less than this value. So the concentration of sulfide ions has to be less than that. And that would bring down the KSP. All right. So now let's look at our other reaction. Um, what do we have here? So for part two, let's put part two now. And let's calculate the concentration of hydronium needed to decrease this concentration, right? Because we have to bring that concentration down in order to have this shift to the right. Well, we already have our concentration of S2 here, so let's take a look at this Ka value. So if we set up our Ka is equal to H3O plus squared S2 minus over H2S. And we're given, there it is, we're given this concentration here. So we know the concentration of H2S is 0.10. We just calculated the concentration of here. So we can now calculate this concentration by putting all this information in. Our Ka was 1.0 times 10 to the minus 26. There we go. All right, so let's plug in all these values and see what we get for H3O plus. So concentration of H3O plus squared uh, times the concentration of, so that's going to be 2 times 10 to the minus 26 over 0 is equal to 1.0 times 10 to the minus 26. Let's go ahead and clean that up. Rho divided by 2 times 10 to the minus 26, and that value equals 2. So there is our concentration here. Now let's understand this. So if we're looking at these reactions, the only way that I can decrease this concentration is by increasing this concentration, right? If I so if we increase this concentration, we decrease this concentration, and that will shift this reaction to the right and prevent precipitation. So here our concentration, so H3O plus has to be greater than 0.22 molar in order to present precipitation from these two reactions mixed together. Let's see. I gave you part of some information earlier here. So let's see. I guess we're gonna try and we're gonna work this back. We're not gonna try, but we are gonna work this backwards. Is we'll say what's the molar solubility? So what's the molar solubility of some barium sulfate in a 0.250 molar solution of Sodium hydrogen sulfate. All right, and let's give you some information here. So we're going to say that the Ka here is equal to 1.2 times 10 to the minus 2. 1.2 times 10 to the minus 2. And as soon as I see that, K is less than 1. It is not a lot less than 1, which means that we are not making an assumption because K is just less than 1, but it's definitely not a lot less than 1. All right, so we'll come up with our two reactions here. So the first reaction we're going to need is barium sulfate. Oh, put a solid here. Let's see. Then we're going to need a second reaction here. Sodium's a spectator ion. We're going to put this in water. All right. So we have some common ions here. And let's see, we have concentration. All right, so here, I'm going to draw the ice table down here. So this is the ice table. I drew a little arrow for that. So this ice table here, I'm going to ignore that. Oh, I don't need to draw that here. Concentration of, what's the molar solubility of in a 250 molar solution? I think I wrote down the wrong. Let's see. 250 molar solution of sodium hydroxide. We're working backwards here. So here we don't need this here, and we're going to go 0.250 concentration of hydrogen sulfate. We don't have any here. We don't have any here. And then as normal, we go minus x plus x plus x, and this is going to be 0.250 minus x, x, x. All right. Um, so here we're not making an assumption. We have the Ka, and we're not making an assumption here. So let's go ahead and set up our Ka. So our Ka is equal to x times x over 0.250 minus x. And this is equal to 1.2 times 10 to the minus 2. 1.2 times 10 to the minus 2. X squared, 0.250 minus x. Oh. What is x equal to? X is equal to 0.049. Other than that, you would be expanding this out, doing the quadratic formula, figuring that out, or use the solver on your calculator. I use the solver on my calculator here. But if not, we have to recognize that you do have to use the quadratic formula for that. All right, so we have 0.049 is x, so we now know that concentration, right? So concentration of our common ion here equals 0.049 molar. All right, well, if we're going to calculate the KSP, right, what's the molar solubility of? We're going to have to look up the KSP. But remember, our KSP is how we figure out molar solubility, right? KSP of this molar solubility of barium, right? So we're asking for molar solubility, right? This is what we're looking for, molar solubility. Let's see if we can look up the KSP. Hopefully we have this KSP here. Barium sulfate, KSP. Nope, way. Ka, Kb, KSP. We had barium. There it is, 2.3 times 10 to the minus 8. Perfect. So our KSP is equal to 2 times 10 to the minus 8. And we know that the KSP is equal to barium 2 plus our sulfate 2 minus, and this is equal to 2.3 times 10 to the minus 8. Well, we now know this concentration, so we can plug that value in. And we'll make that calculation. Oh, let's see, 2.3, 8, 10 to the minus, to the minus 7. All right, so we figured out what this molar solubility is. So again, we do have to remember, right, when we're looking for molar solubility, you guys are given all these terms this chapter, um, a bunch of Ka values, KSP, Ka, Kb. When we're calculating, understanding these terms, we have to remember what it is we're actually calculating. So this one is actually the reverse. So we did this problem here using uh, using the KSP. So we used the KSP to calculate some concentration, and then we just did the reverse reaction right here, where we're using the concentration to to calculate the molar solubility. And I think I just have maybe one more reaction for you guys. Yes, Elisa?
Sorry, instructor. I
No, it's
have
okay.
a question. It's kind of stupid, but
No, 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 no.
um,
It's not stupid.
so for the sodium sulfate, why do we assume that the 0.250 molarity are gonna just be for the hydrogen sulfate?
Uh, I'm looking at this keyword here. A 250
Okay.
molar solution of
That. Oh, okay. Oh,
that.
because that's so. Okay, so if that would be in a solution, then the sodium will dissociate from it.
Yeah, the sodium dissociate. It's just a spectator ion. So it's just
Oh,
a
oh,
spectator ion. Yeah, we don't
yes.
need. Yeah, it's just a
So
spectator
okay,
ion. We don't even worry about it.
yeah, okay. Thank you. Sorry,
Uh
that
huh.
was the only
No,
thing that I was like,
no
wait.
problem.
Thank you.
Uh huh. Let's see. Let's calculate molar solubility again. So let's calculate molar solubility. but we use aluminum hydroxide in a 0.100 molar ammonia solution. And let's give some different information here. How about the concentration? I'm going to give you some additional information here. We'll say the concentration of NH4 is equal to 0.400 molar. And let's use the KB, 1.8 times 10 to the minus 5. Calculate the molar solubility. Calculate molar solubility of aluminum hydroxide in a zero point 0.1 molar solution of ammonia. All right. So if we're looking at that, so let's go ahead and take a look at our base, right? We recognize NH3 as our base, and what do? We simply just put it in some water. And we're going to get NH4 plus aqueous, plus we're going to get some, plus we're going to get some hydroxide. So that's one reaction. Our other reaction we're going to need is the aluminum. So we'll take some aluminum hydroxide, solid. Right, we see that common ion there. If we're given the KB, let's look at that first because we are given the KB. KB is equal to, let's see, we're going to have NH4 minus over concentration NH3. So fortunately for this one, we're actually given two concentrations. We're given concentration of ammonia, we're given concentration of ammonium, making this just a lot easier here. And this Kb equals 1.8 times 10 to the minus 5. So let's just go ahead and plug in our values that we actually have here. So this is going to equal 0.400 times this concentration here. Concentration. What was this? 0.00. All right, and if we go ahead and clean that up, 1.8 times 10 to the minus 5, 0.100, all over 0.400. This equals 1.8 times 10 to the minus 5. 4.5 times 10 to the minus 5. All right, so we now know this concentration. We know the concentration here is equal to 4.5 times 10 to the minus 5. And if we look for the KSP here, we're going to probably have to look up the KSP. So I don't have it. Let me look that up here. So our KSP is equal to concentration of times the concentration of this to the third, though, because we have three of those. Yes, to the third. And let's look up let's see, aluminum hydroxide. There it is. Perfect. 2 times 10 to the minus 32. 2 times 10 to the minus 32. Uh, let's substitute our values in. So no ice table needed. We got 4.5 times 10 to the minus 5. And this is to the third equals 2 times 10 to the minus 32. right. There's some practice for you guys. Let's see. Negative 32 by 4.5 to the minus 5 to the third. And check my math. 2.2 times 10 to the minus 19. Is that right? Yep, 2.2 times 10 to the minus 19. So we've calculated the molar solubility of aluminum. All right, good, 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 good. All right, that is, so we've covered chapter 15 now. So we're all done with chapter 15. Let me stop this recording